Yes. In this video, we want to cover the last chapter on the topic of distribution functions and random variables. Namely, we want to introduce the concepts of median, quantile, and independence in the context of random variables. We have already learned the terms in the context of events, and exactly. We now need to redefine these terms, so to speak, for this new concept of random variable, and we start with the concept of the p-quantile. This goes as follows. So we assume that we have a given random variable. It can be continuous or discrete. We call it x, and we have a value p. What our p-quantile is between 0 and 1, then we call a value xp, which is still a real number. It is called p-quantile when f of xp equals p. And that means median when we choose p equal to 1.5. And let us think about this briefly. Why? This corresponds to what we previously discussed regarding the quantile of a sample. And what we have said is that a quantile is something like this. We have a sample and then we have a value here. And p. The proportion p is here, and the proportion 1 minus p is on the right side. And if now f of x, p equals p, then that means if I write it out that p is the probability that x is less than xp. And, well, that means exactly I want to look at what the probability is of this left part of this value xp and the value itself, yes. This is called the median, so not the p, but the xp, is called quantile. And for p equal to 1.5, it is the median. Thus, we see that it is a natural generalization. And we also want to do an example right away. But before we do that, just a brief note. It may be that p-quantiles do not exist, so we are not. It is just because we have a random variable does not necessarily mean that these p-quantiles must exist. And above all, they do not have to be unique. It is also possible for multiple values to be p-quantiles. You might still remember our example with the sample where we have two values, and then we calculate the arithmetic mean. It does not generalize so easily. So it may be that there are also two values that are a p-quantile, or even no value at all. Alright, let's calculate an example. We have our following distribution function. It looks similar to the one we had before, only this time k is equal to 1. And we are now to determine the 0.6 quantile. How do we do that? We write down the equation. We want f of x to be 0.6, so it should be 0.6. That means 1 minus e raised to the power of minus x 0.6 is equal to 0.6. Then we do minus 0.6 plus e raised to the power of minus x 0.6. So what we are doing is we want to solve for x 0.6. And there you can already see the problem when the function f is relatively complicated. It may be that it is not possible to solve it at all. If it is a fifth degree equation, then we cannot solve it. And with that, you can already see the problems that can arise here regarding existence and uniqueness. But we are lucky. Let's calculate this a bit further. What do we have then? We have e raised to the power of minus x 0.6 equals 0.4. Now we can apply the natural logarithm to both sides. This is how you solve such an equation. So we have minus x 0.6 equal to parts log 0.4, and then we are done. Now we just need to move the minus to the other side. Minus log 0.4. And now just enter it into the calculator and you will get the result. Yes, this is, so to speak, how you can also determine p-quantiles for distribution functions. As mentioned, we were fortunate in this case that the function was solvable for xp. This does not have to be the case in general. However, you might still be able to obtain a numerical value. But you also see that there can naturally be multiple solutions for the equation, or even none at all. That is also possible. Alright, that's it for the p-quantile for now. The next concept is that of the independence of random variables. Until now, we have discussed the independence of events. The concept of independence of random variables is a bit more general. Let's take a look at the whole thing from the definition. So we have two random variables, either continuous or discrete. They are called independent. If. And now let's try to break this down to events. If the events x belongs to A and belongs to B, we will take a look at what these events are for all possible sets, A and B being independent. Okay, let's stay there for now. So we say two random variables are independent. If we take arbitrary sets A and B, we can form these events here. And these events are supposed to be independent. And what independent events are, we have already learned. Okay. Yes, and that means, or we have learned that, in other words, it means that this probability here is equal to the product of these probabilities. And now we need to briefly consider, what is the event x belongs to A? Well, these are all the elements from omega that, when I substitute them into x, yield an element from A exactly. Of course, it is indeed very, very difficult to verify whether that is the case, because you see, we need to try to achieve this for all possible sets A and B. This is very difficult. Yes. And that's why there is also a statement that makes our lives a little easier. It is the following. It says that it is sufficient to consider specific events. We do not need to look at all events x element A and y element B. The following. Statement says that two random variables are independent if and only if the events x less than or equal to x and y less than or equal to y are independent. So we can reduce to x less than x and y less than y for all x, y in R. These are therefore specific events of the form x belongs to A, y belongs to, and that is quite good. In other words, it is sufficient to break it down to these events. And for discrete random variables, it is even sufficient to break it down to the events x equals xi and y equals yi for all arbitrary values that can be assumed, xi and yi. Yes, so this is, so to speak, even less that we need to check. Again, when we have a discrete random variable, it means we have only a finite number of values that can be assumed, and it is sufficient that you only consider x equal to xi and y equal to y, which are both events that demonstrate the independence of these events. This is already a bit simpler, and let's also do an example right away. Overall, it can be said that this is quite a relatively abstract area, and you might need a moment to digest it. So, please listen to this again and see, so to speak, the connection between the independence of random variables, how we break it down to the independence of events, and also see how strong this definition is, because it must indeed be the case that very, very many events are independent of each other, so that the random variables are independent. Now we will do an example, specifically looking at a discrete distribution, namely the roll of 2 dice. We will examine the random variable x, which is the number shown on the first die, and the random variable y, which is the number shown on the second die, because yes, or we will ask ourselves whether these are dependent or independent random variables. But intuitively, it should be clear that they must be independent random variables, because die 1 has nothing to do with die 2. There is no secret connection between the two. Now the question is how one can prove this, so to speak. And what we essentially need to do is to show that these events, x equal to xj and y equal to yj, are indeed the two events that we want to consider together. And they are independent of each other. And how do we do that? We need to determine the probabilities. Let's determine the probabilities. We can first determine that px is equal to xj. So, imagine a number between 1 and 6. It doesn't matter which number, because they are all equally likely. That means we can do it in one go. This probability is 1/6, right? Logical. And the same applies, of course, for y equal to yj. That is also 1/6. And let's take another look at the definition. We need to now, so that was that, and that was that. And now we need to look at the probability of the intersection of these two events. And we will do that now. X is equal to xj intersected with y is equal to yj, and let us think briefly. This means that x is equal to xj and is equal to, well, if I have 2 dice and I specify exactly 2 numbers, there are a total of 36 possibilities, and exactly one possibility is the correct one, which means that is 1 out of 36, and that is equal to 1/6 times 1/6, which is px equal to xj times py equal to yj. And with that, we have shown that dice 1 and dice 2 are independent, random variables, meaning that the outcomes are independent of each other. That was the topic of random variables and distribution functions. I hope that you have managed to keep up somewhat, and I look forward to your questions in the next lecture. Take care.